So the talk I'm giving today is about deep homogeneous mixture models. So this is a term that we sort of invented a little bit. In particular, I'm going to be talking about the representation of such models and the separation and how do we approximate them. So this is a joint work with my student Priyank and my colleague Pascal at Waterloo. So I started working on this for two motivations. The first one is trying to understand the power of depth in modern deep networks, and also trying to understand how can we sort of go beyond just representing functions, but approximating functions, because approximation is really what you need in practice, right? So this is sort of, for this audience, I don't really need to motivate this. So we know data nowadays is basically everywhere, but data is usually unlabeled and it's unstructured. This is why we need these unsupervised methods to help us comprehend the data. And there are lots of recent progresses in the machine learning field. I'll mention maybe a few of them. And in particular, I'll be focusing on a very classic problem in statistics in machine learning. And this is known as the multivariate density estimation problem. So basically here, we're given a data set with x1, x2, these points in a Euclidean space. And we want to find a density function, P, in a class F, such that these trending points xi roughly follows the density function P. And of course, once we have the density function P, we can do lots of things, right? For instance, we can generate new data, and we can use this new data to help us train better models. And because this is a very classic problem, it has been studied by many people years and years ago. So there are lots of methods you can use to estimate such a density function P. I'm not going to give you an exhaustive overview here, but it suffices to say many people have worked on this for years. And this problem is considered very challenging when the dimension D, the dimension small d here, is large, right? Usually, if you talk to theoretical people, they'll tell you the bounds you get is going to be exponential in terms of the dimension D. So you need lots of training samples in order to get a good estimate. On the other hand, very recently we see lots of work in the machine learning community where people use neural networks to approximate these density functions. And these results are surprisingly effective, right? It seems like we have bypassed the curse of dimensionality. And the one motivation of this work is try to understand what is really going on with these neural networks. Okay, so this is just a very quick overview of what people have done for estimating density function in the machine learning community very recently. So there's one work by a good fellow and his co-authors in 2014 where they proposed the generative adversarial network. So in this type of methods where basically you try to transform a source distribution, which is usually a noise, to the target distribution, a distribution that you want to estimate. And the difference is they usually do not represent the density function explicitly. You only get an implicit representation, so you can sample from this implicit representation, but you cannot write down the formula of the density function. This is both good and bad depending on what kind of applications you use these methods. There's another approach which I call the explicit density estimation. There are roughly two categories. They are very closely related to each other. One is the so-called autoregressive models. Here, basically, you take a density function of a bunch of variables, and you just factorize them using the usual Bayes rule. Right? You just write them as a product of each variable conditioned on the previous ones. And now you can try to model these conditional distributions with a particular neural network unique. And this has been tremendously successful in terms of modeling images, for instance, the pixel RNN or pixel CNN, and so on and so forth. I should mention that many people here in this institute have also worked a lot on these type of methods, right? So the other approach would be what I call the transformation approach, where you take a noise distribution, usually it's just a standard normal distribution, and you find a transformation function T, such that after transforming your noise, you can model your data. right? And usually people put some assumptions on T such that you can do the computation easily, you can invert the computation easily. So lots of work have been developed for this category. So, we have also worked on this a little bit recently. So what I'm going to talk about today is a very, very classic approach known as the finite mixture models. So here, you just represent your density function P as a convex combination of some predetermined density functions Fk. So Wk, these are non-negative, they sum to 1. So it's a convex combination of existing density functions. Here's an example where suppose this is your data in a two-dimensional space. You can have 3 components. You have F1, F2, F3. And then you combine them, you get you can model the data fairly well. And the good thing about the finite mixture model is it's very simple, and it's very easy for you to explain the result. Like if I look at the picture here, it's clear to me that there are 3 components. Now I can try to interpret these components very easily. And they're also universal in the sense that given any density function, and as long as I can choose k to be sufficiently large, then I can approximate any density function arbitrarily well if I choose this Fk carefully. The other good thing about the finite mixture model is they are very efficient algorithms. For instance, the EM algorithm, if you apply to the finite mixture model, you get very simple updates. And in the machine learning and the theoretical computer science community, many people have been trying to study how tractable these EM algorithms are for these finite mixture models. Okay, so these has been studied quite a lot very recently. So our setup, inspired by the work by Martins and Metabanimi in 2014. So this is the setup of our work. So we take a variable x that consists of x1, x2 until xd. So you have d variables. Each of them is in a space. So you can think of xi as a real number. Okay, so I have d of them. And for each variable xi, I'm going to have a class of density functions. So I'm going to restrict myself for this class of density functions for this variable xi. And I'm going to have a so-called tensor, density tensor. So this is basically a multi-dimensional array. So if it's 2D, it's a matrix. If it's a 1D, it's a vector. So I have this tensor, which is non-negative. Each entry is non-negative, and they sum to 1. Now, given these Fi and this tensor W, now I can define the so-called homogeneous density mixture. So it's given here. It's basically a summation of these weights given by the tensor W, and I have the product of these functions. So the product is basically saying, for each variable xi, you take a function, and then you just multiply them together. Okay, so if I use a probabilistic language, if you look at the function here, this is actually a density function, and the marginals on each xi, they're independent, basically, because I'm multiplying them together. And then you just combine them with these coefficients, because they sum to 1, so this is, again, a very valid density function. And sometimes we use this shorthand for this very complicated formula. Okay, and it's very clear from the definition that this homogeneous density mixture is a finite mixture model, because you can think of this as a Fk, and then you have many Fks, right? So this form is exactly in this case. In particular, if you put these indices to be a constant 2, then basically we are summing 2 to the power d density functions here, right? So you can sum a lot of these components. And this is, in fact, a very simple, a well-known tensorization trick to go from a univariate function to a multivariate function. You just take a bunch of univariate functions, and you do the so-called tensor product, you get a multivariate function. So it's a very simple trick. And this is what we call a homogeneous density mixture. And, and here's a very simple example. So I have a density function fx written in this form. So what we can do is take these functions on x1. So I have 2 functions on x1. F1, F2, and then you can put them together in a vector form. And you take all the functions of x2, I have 3 of these functions, g1, g2, and g3, and you put them in a vector form, right? And then you take these coefficients, 0.2, 0.3, 0.5, you put them in a tensor W, okay? And in this case, then I can rewrite my function f as the dot product between this tensor and this very complicated matrix of functions here. Okay, so this is what we mean by homogeneous density mixture. And so you may have noticed that I call this homogeneous. Why? Because in this formula, if you look at the product for each variable xi, there's only one function depends on xi. This is what we mean by homogeneous. For instance, if you take this f to be, if you remove this x, then what you get is basically a homogeneous polynomial. That's why, yes?
Is this just a special case of a sum product network?
Yes, I'll go back, I'll come back to that. Yeah, we'll see. This is, in fact, more general than sum product network. It's actually a subclass, sum product network, a subclass of this. So the next thing I'm going to show you is the various probabilistic models that we use in machine learning. They're all special cases of this homogeneous mixture model. So this is sort of a unification of existing methods. Okay, and as I said, the reason we call it homogeneous is because this is sort of like homogeneous polynomial here. Okay, and if you don't like homogeneous polynomial, you want to have inhomogeneous polynomials. It's also easy to do that because it is a well-known homogenization trick that can lift an inhomogeneous polynomial as a homogeneous one. So this is sort of without loss of generality. And the one nice thing about homogeneous mixture models is if you choose these functions that all depend on one variable, if you choose them carefully to be universal, meaning that if you can approximate any univariate function with these fi's, then what we are doing here is basically a tensor product. Then we can actually approximate any multivariate functions arbitrarily well. Okay, this is a very simple result proven by Sharia et al. in this year. And this is what I said before. So I'm actually going to show you why this is important. In fact, many models that we are familiar with, they are special cases of this. Okay, so this is one, sort of the first part of this talk. And this is a very quick sanity check on why this is useful. So you see, here I'm giving you a very simple example. I have a mixture of normal distributions. I have 4 normal distributions. And they are having the full covariance matrix. This is the covariance matrix of the component 1, the covariance matrix of component 2, 3, and 4. And now what we're going to do is we take these mixture model, we generate the samples, and then we learn a homogeneous mixture model, okay, using this data, training data. And the algorithm we use to learn this homogeneous mixture model, I'll give them in the end. Yes?
Isn't it in a sense what distribution flow, the maximum likelihood with the distribution flow doing? Basically breaking dependent or any arbitrary distribution?
Yes.
Dependent component?
Yes. Right, you're right. You're absolutely right. So in fact, the algorithm I'm going to talk about in the end, or what we're using here is basically what you said. You take the data and you're basically trying to construct sort of an independent component of it, and then just continue doing this. In the end, you can approximate it. Yeah. So what I'm showing here is even with full covariance matrices, you're using this sort of combination of independent sort of homogeneous ones. It's quite effective in the sense that only after like 4 or 5 iterations, you can actually approximate these mixtures fairly well, even though they have full covariance matrix. And we're just combining densities with diagonal covariance matrix. Okay, so I hope this can convince you that this model is useful and worth studying. So this is the outline of the talk. I'm going to show you, as I promised, the various models that we use in machine learning. They are actually special cases of the homogeneous density mixture. In particular, there is actually a hierarchy of these methods that we know. And then I'm going to talk about the separation, namely that if you take these homogeneous mixture models, if you make them deep, I'll explain what I mean by making them deep, and how can you increase sort of the capacity or expressiveness of these models. And then I will go to the approximation where we don't want to have an exact representation, but an approximate representation, and how things will change. Okay, so this is a summary of the result I have from the first part, where basically we take the existing probabilistic models. Here I'm giving you the so-called tensorial mixture model. This is proposed by Sharia et al. This year. And this is the hidden Markov model that is familiar for most people. And this is a latent tree graphic model that if you know graphical models, this is a very popular one there. And this is what we call a tensor format. This is being used in the numerical linear algebra field. And this is what Jimmy mentioned. This is a sum product network. So in fact, these models, you can put them in a hierarchy. So the one is contained in the other, basically. Okay. So before I discuss this theorem, let me go through these models one by one so that if you haven't seen this before, you will have some idea. So sum product networks. This is first studied by Darwish and Poon and Domingos. It's also known as the arithmetic circuits in the theoretical computer science field. So basically, a sum product network is a tree. It's a rooted tree. You have a root at the top, and at the leaves, what you see are basically functions. Okay, in our case, these functions are density functions. So I'm using this double index here. So for the superscript, it means it's a function of x3 here. Okay, so different super index means that it's a function of a different variable. The sub index means it's a different function of the same variable. And so the leaves are functions. And then all the internal nodes, you have the sums or products. Okay, so if you see a product node, what it means is you multiply the children nodes. If you see a sum node, you just do a weighted combination of the children nodes. And this is what is known as the sum product network. And the computation usually is bottom up, so you have the functions at the end, at the leaves, and then you just go one level up, you compute. At the root, you output the result. Okay? And in particular, there is a special class of sum product networks. This is known as a complete and decomposable sum product networks. They are useful because if the network is complete and decomposable, then it's guaranteed, if you put density function at the leaves, it's guaranteed at the top, you're getting a distribution function. Okay, and there are also computational consequences of this. So for completeness, it means if you look at every sum node and look at these children's, they must have, if I use a neural network terminology, they must have the same receptive field. So if I look at this sum node here, it depends on the first variable, the second variable. Now if I look at this branch, it depends on the first variable and the second variable. Right? Different branches of the sum node, they must depend on the same set of variables. They have the same receptive field, basically. Now if you decomposable means if you look at a product node, then they must have non-overlapping receptive fields, basically. So if I look at a product node here, this one depends on the first variable, this one depends on the second variable. They cannot overlap. So this is what it means for SPN to be complete and decomposable. In fact, what I'm showing you here, these two figures, they represent the same SPN. It's just written differently. Okay? So this is what we call a self-similar SPN. This is a general SPN. So a self-similar SPN means if you look at the children of every sum node, they look very similar. So it's like they're copying each other. Whereas if you look at the sum of this one, they're actually different because the variables are different. Okay? So why do we care about sum product networks? There are a variety of reasons. The most important one is for most graphic models, it's very difficult to train and it's very difficult to do inference. Whereas for sum product networks, inference takes linear time because when you do inference, you just need to compute at the top, at the root. What you do is you insert the values at the leaves and then just propagate along the network. And when you arrive at the root, you get your result. Right? So computation is linear time in the sense of the network size. And also, you can easily do conditioning. You can easily do marginalization of the underlying distribution if your sum product network is complete and decomposable. And due to the work of Delalue and Benjil in 2011, what people realize is these sum product networks, they can effectively combine many component mixtures in a very, very effective way. And the intuitive reason is you're doing the computation in a hierarchical way. So now if you expand at the very top, what you're going to see is a lot of sums in the end if you expand at the root. And this is why you can combine lots of things in a very hierarchical and efficient way. I'll come back to this work by Delalue and Benjil. Okay, so this is SPN. Okay, I hope I'll give you a quick sense of what is the SPN. And the next one we talk about is the so-called hierarchical tensor format. This is mostly from the numerical linear algebra field. It is a wonderful book by Hagerbusch about these formats. So in a nutshell, what a tensor product means is you take two spaces, V1 and V2, and then you can compute the tensor product, define the tensor product. Basically, you take one vector in one space, another vector in a different space, you do the outer product, and then you just sum a bunch of these together. Okay? So this is what is called a tensor product. And the important thing is, for tensor product, for instance, if V1 is a function of x1, if V2 is a function of x2, now by doing the tensor product, now you get a function of x1 and x2. Right? This is a very simple way to sort of go from a univariate function to a multivariate function. And importantly, the dimension of the tensor product is the product of the dimensions. Okay? So this is, in a sense, undesirable because when you do the tensor products, the dimension of these spaces will increase very, very quickly. And in a hierarchical tensor format, what you do is you compute the tensor product, and then you truncate the dimension. So you don't keep all the bases in the tensor product. You only keep, say, constant number of bases there. And this is called the tensor product, a hierarchical tensor format. Here's an example. If you take a function space of the first variable, the second variable, the third variable, and the fourth variable, and each function space has dimension 2. So here I'm using a superscript to describe the dimension of the space. Now if you compute the tensor product of this one and this one, you're going to get a function on x1 and x2. And if you just compute the tensor product, the dimension here should be 2 multiplied 2, that's 4. But in hierarchical tensor format, you truncate. You don't take all the bases, you only take 3 in this case. And similar here, and then when you get these two, you can do a tensor product again, then you get a function of x1, x2, x3, x4, and then you truncate the bases from 3 to 1. And this is what a tensor format does. And on the right-hand side, what I'm showing you is actually an equivalent representation of this hierarchical tensor format, but written in the sum product network form. Okay? So these sort of structures, they are actually equivalent to each other. So latent tree graphic model, this is probably familiar to most people here. Again, you have a rooted tree, and at the leaves, what you have is these so-called observed random variables. Here you have x1, x2, x3, x4, and then the internal nodes, these are hidden nodes. Right? You don't actually observe them, and usually we assume the hidden nodes, they take finite number of values. What I'm showing you on the left here, this is the so-called tensorial mixture models. Basically, each time you take two variables and you put a hidden node. You take two variables, you put a hidden node, and then you take two hidden variables, you put another hidden node. This is known as the naive Bayes model, where you have all the observed variables, but you only have one giant hidden variable, right? And this is known as the hidden Markov model, where you have observed variables and you have one hidden variable, and then you have one observed variable here, and then you go one level up, you get another hidden variable, and you get another children as the observed variable, and just continue doing this. So the tensor mixture model, naive Bayes model, and hidden Markov model, they're all special cases of the latent tree graphic model, right? Because they just give you different trees, latent trees. So you can have all kinds of these latent tree graphic models. So okay, so now I have explained to you what is an SPN, what is a hierarchical tensor format, what is a latent tree graphical model. So now I can explain what the theorem says. So basically what we found is, of course, every hidden Markov model, for instance, is a latent tree graphical model. And in fact, any latent tree graphical model, you can convert that into a hierarchical tensor format. And any hierarchical tensor format, you can convert that to an SPN. Okay, so there is this hierarchy between different models. And in fact, the conversion here, if you go from a lower class to an upper class, the conversion is actually very straightforward. It takes linear time. It doesn't increase anything. Okay, it's very straightforward to go from a lower level to an upper level. And we also have reasons to believe in an upper class is strictly more expressive than a lower class. Okay, so proving this formula is a little bit tricky. We're still working on that, but we believe that's the case. Okay, so this will end the first part of my talk. It's basically we take the existing models that people have been studying in machine learning, and we try to sort of give them a unification here. And the nice thing about the representation theorem is the following. So now, if I can prove something difficult, say for a latent tree graphical model, then immediately I know the same difficulty will happen for some product networks, because any latent tree graphical model is a sum product network. Right? So now, in terms of understanding how hard we can learn these structures or how easy we can learn these structures, we can take advantage of the representation theorem. On the other hand, if I develop an algorithm for some product networks, then automatically I have an algorithm to learn a latent tree model. Because I can take any latent tree model, I can convert that into a some product network, and then I can apply my algorithm for some product networks. Right? So this representation here gives you the flexibility to sort of to reduce many things into one thing, and you can only focus on that one thing. Okay? And this is what, in fact, what we did, and this is what I'm going to explain next. So by using this unification, you can actually try to understand how powerful each of these models are. And this is a sort of an intuitive picture. What I'm showing you here are three different graphic models. This is the so-called tensor mixture model. This is a naive Bayes model. This is a hidden Markov model. If you just, of course, I'm only showing you x1, x2, x4, the 4 observed variables. Now, if you look at these structures, it is intuitively clear this is very shallow because you only have one hidden variable. And these two structures, they are quite deep in the sense that you have levels of hidden variables, right? So you have this dilemma between choosing a shallow network and a deep network. In fact, this is very well-known difficulty in the graphical model literature, where people try to understand, should I have more hidden variables, or should I put more values in each hidden variable? Like here, this hidden variable can take, say, 8 values, right? This hidden variable maybe can only take 2 values. So should I have more hidden variables, or should I allow each of my hidden variables to take more values? So this is sort of a trade-off, a dilemma that people try to understand. And in fact, our work would indicate that you should have more hidden variables rather than having more values. So, okay, I'll skip this. So we have talked about these architectures, they are basically equivalent. So the idea of proving the fact that a deep architecture is more powerful than a shallow architecture is to go back to our representation theorem. So we can actually reduce any of these models to a tensor format, a hierarchical tensor format. And the reason for doing this is, once we have a tensor, it's an algebraic object. And there are many techniques we can use from multilinear algebra to bound the complexity of tensors. And this, in fact, has been well studied in numerical linear algebra. So now we can take advantage of these results and prove similar things, say, for SPNs, for latent tree models. And this is, in fact, what we did. So the first result we showed is basically characterizing the complexity of a very shallow SPN. So let me give you an example here. So this is what we call a shallow SPN. So you have the leaves as the functions, and then you have one layer of product nodes. And at the very top, the second layer, you have a sum node. That's it. You can have many product nodes in the second layer. Okay? So what this theorem says is, if you want to represent a density function, which we represent as a tensor W, and with this structure here, then the number of product nodes you need is exactly the rank of the tensor W. Okay, so how many product nodes do I need in order to exactly represent this density? That's the rank of this tensor W. On the other hand, if I allow myself to have a layer of sum nodes first, and another layer of product nodes, and at the very top, I get a sum node again. Okay, so now instead of having one layer of product nodes, I'm having one layer of sum nodes, I have another layer of product nodes, and at the very top, I have a sum node. So in other words, this one looks deeper than this one, right? Because this is a 2-layer network, this is a 3-layer network. And what we prove is, if you're going to represent a density function with this architecture, then the number of product nodes you need, the number of product nodes you need is the rank of W. And if you want to represent in this architecture, the number of product nodes you need is the number of non-zeros in this tensor W. I said it opposite in the beginning. Apologize for that. So what does it mean? So basically, if you represent a density function in this architecture, the number of product nodes you need is the number of non-zeros in the tensor. If you go to here, it's the rank of the W you need. And this is where you see that even adding a layer of sum nodes can increase the expressively a lot. And the reason is, if I go back here, the number of non-zeros in a tensor W is much larger than the rank. And this is known. And in fact, you can actually prove that for a significant number of tensors, the number of non-zeros is much greater than the rank. Okay, in other words, if you want to represent your mixture model, this one, if you represent it in this way, the size of your network in terms of the number of product nodes is much fewer than representing in this way. Okay, and this characteristic is actually exact. So this rank and this number of non-zeros is exactly the notion you need to characterize the complexity of these shallow networks. And the next thing we did, I'm not going to read this. So the next thing we did is, what if I'm going to represent my density function in a deeper network? So here I have 2 layers, here I have 3 layers. What if I represent it as, say, 10 layers? What happens, right? And the result we found is the following. I'll give you the special case of the theorem we proved, namely that if you look at the structure you have, so here I'm using the latent graphical models as a latent tree graphical model as an example. So if you look at how you form the latent tree graphical model, you look at each observed variable. Okay, so like x1, x2, x3, x4, and you count how many siblings each observed variable xi has. In this case, if each observed variable has, say, b observed siblings, then you can actually prove the rank is at least r to the power of d by b. So in this case, each sibling, each observed variable xi has 1 sibling. So b is 2. So the rank is at least the r to the power of d divided by 2. So in other words, if you want to represent this with a shallow network, then the size has to be r to the power of d divided by 2. And that's exponential in d. Similar things for the Hillenmacher model as well. where each observed variable has only one, has no sibling at all. Okay, so this result in fact was proved by Donano and Bangio in 2011. In fact, I think this is the first work that showed the benefit of depth, okay, in the context of some product network. And this work, of course, after this work, it inspired another work on showing the benefit of depth in a neural network as well. The original SPN constructed by Donano and Bangio is the following network, where this is SPN, but it's not a complete SPN, because if you look at the sum node, they do not have the same receptive field. Right? Here you have the receptive field x1, x2. Here you have the receptive field x3, x4. They do not have the same. In other words, the original proof by Donano and Bangio does not work for a complete and decomposable SPN. This was later extended by Martins and Metabanani, and in particular, Sharia et al. Proved that the example constructed by Donano and Bangio was in fact not pathological, okay? Because what Donano and Bangio did is they construct a network, a particular network that cannot be represented efficiently by a shadow network. But there is a possibility that this constructed network maybe do not appear in practice at all, right? It's not useful in practice. And what Sharia et al. Did was to rule this possibility out, because they proved that, in fact, it's not just this particular example, it's actually almost every sum product network has this property. And in fact, the interesting thing is this existing result and this almost sure result is actually equivalent. So if you can prove one network has this property, then almost every network has this property. Okay. So what we did is basically we generalized the result of Sharia to any tree instead of a fully binary tree. Okay, so that's all I want to say about the representation. But the next thing I want to show you is, what if I'm not interested in an exact representation, right? All the results here says if you have a density function, and you want to represent this density function exactly using a shadow network, then the shadow network has to be very big. This is what these results say. What if I want only an approximate representation of my density, right? In reality, this is what matters. And the things are actually very different if you go to approximate representation. And this is, again, why the tensor format sort of interpretation is useful, because now we can reduce this problem again to tensors. So what we do is, if you have a density function represented by a tensor z, so now all we need to do is, I want to approximate this density function z by another density w, and I want the approximation to be close in terms of some distance, at most epsilon, right? And we know the rank of this tensor characterizes sort of the size of the network. So we want to have a good approximation whose rank is as small as possible, right? So we can formalize the problem in this way. And in fact, this sort of formalization appeared before, but in a very different context. This is due to Yaoliang. He defined the so-called epsilon rank of a matrix or of a tensor. So what it means is basically, you take a tensor W and you perturb W by at most epsilon, and you look at the rank of the perturbed W, and you want this perturbed rank to be as small as possible. Right? It's basically, you take a W and you look at a small neighborhood and you find the minimum size or minimum rank over there. That's known as the epsilon rank. And what we showed is the following. If you give me a density function, if I want to have an epsilon approximation, then the rank is actually bounded by a constant divided by epsilon squared. Okay, and this has nothing, there's no dependence on the dimension at all. So in other words, if you give me a density, a tensor W, all I need is to have 1 divided by epsilon square sort of network size to represent this. And the proof idea is basically to apply the so-called conditional gradient algorithm to approximate the density W. And the slight downside of the proof is that we actually have to know the target density function f in order to prove this. But of course, in reality, you won't be able to know the target density. And this is why we developed an algorithm to achieve this 1 over epsilon squared bound. And the idea is the following. So suppose H is my target density. I want to estimate H. What you do is you start with a network G, okay? And then you update, you increment the network G by another network F. And what we're doing here is we're basically taking a complex combination between the current network G and the next, another sort of rank 1 network F. And you just repeatedly do this, and then eventually you'll converge. And in fact, you can prove the convergence rate is 1 over t. So after t combinations, I can reduce the KO divergence between the target H and the GT by 1 over t. And the nice thing about this theorem is the KO divergence between H and my estimated GT, this one can actually be estimated. Because if you expand the KO divergence, all you need, you're basically doing maximum likelihood estimation, right? So if you can sample from H, if I have a training data from H, I can actually estimate the KO divergence. Therefore, I can actually optimize this. And this is why this algorithm is practical. So I'll show you 2 experiments that we did. So this is where we take samples from a Gaussian mixture model where with varying sample covariance matrices. And what we did is we take an SPN. So basically, we're trying to combine SPNs to approximate this Gaussian mixture model. And in each time, when we combine SPNs, we take different number of layers. For instance, here, if you see a 1 here, so in each iteration, we're adding another 1-layer SPN. Here, this means in each iteration, we're adding a 2-layer SPN. And the message here is, if in each iteration, you're adding a deeper SPN, the number of iterations you need, or the running time you need, will actually reduce. I mean, in terms of the iteration, it's easy to understand because each time you're adding a more powerful SPN, therefore you need less iterations. The other interesting is up to the number of layers we tried, it also reduces the training time. Okay, so this basically tells you, at least for a reasonable number of layers, if you go deeper, it will make the training a little bit faster. We also tried this on some missing data imputation experiments. So we take these 2 data sets, and then we randomly remove some pixels, and then because we can estimate the density function using the algorithm I just showed you, and then you can actually try to re-impute these missing pixels. This is what we got on the LOB data set. Here, the red curve here is the one where we run the algorithm we had, and in each iteration we're going to add SPN, we add a few. This is where we run 1 iteration, so basically we're combining 1 SPN, and this is the one we get for running 3 iterations. Basically we're combining 3 SPNs, and usually when you combine more, you get better results. On MNIST, we get similar behavior, but the improvement is less compared to the previous one. Okay. So that's all I want to say about, in terms of about the approximate representation of a density function. So in summary, I've presented a very unifying framework for unify the various graphical models that we have in the machine learning community. And for exact representation, there is an exponential gap between a shallow network and a deep network. And in fact, this exponential gap is not just for a pathological sort of a constructed example. It's actually universal in some sense. However, if you want to approximate a deep architecture with a shallow one, then you only need 1 over epsilon square shallow networks to approximate a deep network. And we have a very efficient algorithm to do that. So after this work, we have also been trying to extend this. One thing we tried is to combine these homogeneous mixture models with the so-called transformation methods. So I mentioned the transformation methods before. Basically, you take a noise distribution, you find a transformation so that you can approximate any distribution you like. And usually what people do is that the noise distribution is normal, standard normal distribution, right? And what we initially thought is, what if you change the noise distribution to a more powerful one, right? For instance, I can use a mixture as my noise distribution. Would that make the learning of the transformation much easier? And some of the initial results we got are mixed. It does not always help, but sometimes it can, depending on how you tweak it. We're also working on an extended notion of rank for comparing different networks. So what we have proved now is basically there's a gap between a very shallow one and a very deep one. But what if I take 2 networks, one is say 10 layer, the other is 12 layer? How do I compare sort of the expressiveness of them? You can actually do this by generalizing the notion of rank. And we're also trying to apply this homogeneous mixture model to novelty detection, where you can, because in novelty detection, you're basically trying to find some level set of the density function. So now if you have a more powerful way of estimating the density function, then conceivably you can also estimate the level sets more effectively. Okay, so with that, I will end my talk. Thanks.
Thank you.